So in the previous class, we were discussing about the theory of fundamental load compensation. That actually means we are compensating the load at the fundamental frequency with RLC component. And we were talking about a power system where it has a upstream voltage source and the load bus voltage source, as you can see here. So this is the upstream voltage source with the voltage E, and this is the local load bus voltage B, and between these two buses there is a feeder which is having the impedance of Rs plus jXs, and then this is supplying a load here which is having admittance of GL plus JBL, or you can also write in terms of the impedance 1 by ZL. And this load is demanding the power of PL plus JQL, that is the real power is PL or real load power, and the reactive power is QL. Now the reactive power has to be compensated in such a way that either we get a desired power factor at this bus here, or we get a regulated bus voltage at this bus. So there are two important aspects of the compensation. Number one, the power factor control. Number two, the voltage regulation at the load bus. We will discuss one by one, and we will see that these two functions of the compensator are not independent. Basically, it means that if you have control over one parameter, the others will be not controlled fully. It will be improved or it will be changed depending upon many other parameters. So we have developed this equation in the previous class based on the voltage equation through the feeder impedance. So this equation involves basically quadratic in QS, as you can see. For this value of QS is actually QL plus Q gamma. So Q gamma is here, that is the reactive power compensator or simply compensator. Now why we have denoted the compensator by Q gamma? Because the compensator is purely reactive network. It does not have a real component of the impedance, hence it will not take any real power, or it will not give any real power to the load bus. That's why we have denoted the rating of the compensator or the specification of the compensator by Q gamma. Alright, so this is quadratic in QS. Last time we established this for this relationship of QS, QL and Q gamma, and we can now put the condition that B is equal to E. That is, we want the load bus voltage equal to the upstream voltage source. So B is now equal to E, not in phasor but in magnitude, because we are interested in the magnitude. If the angle is same, the power cannot flow. Therefore, the magnitude of voltage at the load bus and the magnitude of the voltage at the upstream voltage source both are same. Therefore, B is equal to E. Now substitute this condition back into this equation. This becomes E power 4. Okay, and other parameters remain same, and we will solve for this equation which is quadratic in QS. So we can write this equation as A QS square plus B into QS plus C equals to 0. This will give us two solutions, one for plus and one for minus. What is B here? The value of B is this parameter. This is actually B. This is A and this is C. So there are two signs, plus and minus, and we will get two values of QS. We will choose the least value of QS so that the Q gamma rating is minimum. Okay, so the least value of Q gamma is chosen as a feasible solution of this equation. So this is called actually voltage regulation mode, because we are controlling the voltage V is equal to E for certain value of Q gamma. So this can be called as voltage regulation. The compensator is in voltage regulator mode. The next application of this is in terms of the power factor compensation. That is the reactive power control at the load bus. For example, we can arrange the same equation in quadratic of B square. Okay, we will simply square this term here and arrange the whole equation in the order of B square. So if you square this, you will get B4 here, this one, plus RS squared plus PL squared, this is square I am putting it here, and plus 2 RS PL into B square. So this is the square of this term. The next is XS squared, same as here, and PL squared here, minus E square B square. This side we have RS squared, same expression as such. So this is here RS squared plus XS squared into QS squared plus 2B squared XS. Now you can see that this equation is quadratic in B squared. For example, if you see this is B square square, so I can write this thing as simply B squared square. So this becomes B square and whole square. And this is B square here. Okay, it's already B square. This is B square square and this is C. So now this is another equation in terms of the powers of B square. Now we can find out the value of B for given value of QS. For example, we can say that we want unity power factor at the load bus. If we want unity power factor at the load bus, then what we will get? We will get QS equals to 0. Okay, because if QS equal to 0, that is the net reactive power at the load bus equals to 0. That actually means the Q gamma is exactly equal to QL with a negative sign. Or it means to say that all reactive power of the load is supplied by the compensator, and hence the power factor at the load bus is unity. So when I say QS, the QS is taken as the power factor or the reactive power at the load bus. Do not get confused that QS is the reactive power at the upstream voltage source. No, QS is taken as the reactive power at the load bus, or net reactive power supplied by the source at the load bus. Okay, so this condition leads to Q gamma equals to minus QL. Now if we substitute this condition in the previous equation, what do we get? We will get that QS is 0. Therefore, this is remaining term RS square plus XS square into PL square. Alright, so this term is 0 here, only PL square is there. So this is PL square and this is RS square plus XS square. Then here QS is 0, so this is 0. It becomes 2 into RSPL minus E square into B square, and this is V4. So this is again quadratic in B square, you can write this equation as B square square plus A into B square. You can say B into B square plus C equal to 0. And from this we can solve the value of B square, and from B square we can solve the value of B. You can see that B square will have two values, because B square will be minus B dash plus minus B dash square minus 4AC, A dash C dash by 2A. Therefore, it will have two values. When B square have two values, then we will take a square root of that. So actually the solution of this equation will give four values of voltage, and we have to choose the least RMS positive value. That we will see when we solve an example to understand this concept. Okay, so the idea is that you can substitute any value of QS for that you want to design to control the power factor at the load bus, and accordingly you can find out the value of B. That B will be the resultant voltage. You cannot have a control over voltage, but you can have a control over QS or Q gamma. So you can fix the Q gamma to achieve certain power factor at the load bus, but voltage you have no control, and voltage can be solved from this equation. In the first case, we set the voltage and we find out the Q gamma. Here we set the Q gamma and we find out the voltage. So these are two aspects of the problem. Now let us see very important approximation for voltage regulation. In power system, we test its performance in terms of the voltage regulation as well. So we see when the load is being carried by the transmission network or distribution network, what is the change in the voltage at the load bus. Okay, although we can find out the relationship for voltage regulation or change in the voltage by simply putting B equals to B plus delta B. Last time we have solved that equation, and based on that we have found all those previous discussion. So B plus delta B. And what is delta B? B plus IS into ZS. And this I we have solved based on the power actually. That's how that equation came. But here we will develop an interesting voltage regulation expression which is approximate in nature, but it is very useful to understand the nature of the power system. What is here? In this discussion, we will define two important parameters. Number one is called short circuit capacity of the load bus. We call SSC. Now, what is the short circuit capacity of the bus? The short circuit capacity of the bus is actually the capacity of the power system bus that it can deliver the power under fault conditions, mostly the ground fault. So if the ground fault takes place like this here, okay, then this bus is grounded and the current will flow through this feeder with the impedance of the feeder RS plus JXS. So this SSC bar or the short circuit capacity of the bus is E into ISC conjugate. So this voltage into this current. The upstream voltage source or the source voltage into the current conjugate. Now current is here ISC. What is ISC? ISC is EYZSC. As you can find out from this. Since it is fault condition, so this is almost like grounded, and therefore the current will flow like this. So what is ISC? ISC is nothing but E by ZSC, and ZSC is same as ZS because the short circuit impedance will be the impedance of the feeder. So this is EY ZS. This will be E by ZS. So what is ISC conjugate? ISC conjugate will be nothing but the conjugate of the whole thing. So this is E by ZS conjugate. What is that? E conjugate into ZS conjugate. Substitute back here in this expression, we will get the short circuit capacity SSC bar as E into ISC conjugate, and ISC conjugate is E conjugate by ZS conjugate. So E into E conjugate becomes E square. So this is E square by ZS conjugate. Clear? And therefore the short circuit KVA rating or short circuit rating of the source bus is nothing but mod of SSC bar. So this is the mod of this value, and mod of this becomes E square by ZSC mod or ZS. So you can say that the short circuit capacity can be expressed in terms of the voltage square divided by the feeder impedance. So this can also be written as E square by ZS, because ZSC is same as ZS, and that is mod of this. Now from this we can also find out the ZSC or ZS in terms of the voltage of the bus and the short circuit capacity of the bus. Normally this is fixed for given bus. When we design the bus, it has certain maximum current carrying capacity, and based on that, for a rated voltage, this value is fixed. Alright, so value of the short circuit impedance or design feeder impedance will be E square by ZSC. Now once I know ZSC, we can find out RS, we can find out XS. As you can see from the diagram, this is ZS mod, and this will be RS, this will be XS. So RS will be ZS mod into cos phi SC, and XS will be ZSC mod into sin phi SSC. What is given to you normally is the XS by RS ratio. When you solve the problem or when you have any distribution transmission network, you are given the value of XS by RS. Now from this given value we can find out phi SC or phi S is 10 inverse of XS by RS. This is RS here. And once I know phi SC and ZSC from this expression, then we can find out the feeder resistance and feeder reactance. And once we know these values, then we can solve for the previous equations, either for voltage regulation or for power factor correction. Okay. Now, but here we are most interested in terms of the approximate relationship for the voltage regulation. So this expression we have found in the previous class, that delta V is nothing but IS into ZS. And what is IS? Is nothing but PL minus J QL by V equal to B into IL or IS conjugate without presence of compensator. IL is same as IS. So therefore IL is nothing but PL minus JQL by B conjugate. Since B is reference phasor, so B conjugate is same as B and B bar is same as B. So this becomes PL minus JQL by B. And we have replaced the current here in terms of these parameters and solve it. Then we found this is the value of delta V. We divide it by B again. So delta V by B here, and then B square and B square. So this equation becomes delta V by B as RS into PL plus XS QL by V square plus J XS PL minus RS QL by V square. And these two terms are basically real component or in phase component of Br. This is delta Br by B. This is in phase with delta B, and this is delta Bx, that is in phase quadrature with the delta B. So we call it Br, delta Br and delta Bx. Now substitute the value of Rs and Xs and simplify them. So Rs is ZSC cos phi SC. So Rs becomes ZSC here, this one, into cos phi SC and then into PL, this is PL, then plus XS into QL. So XS becomes ZSC into sin phi L here into QL. Now delta Bx is assumed to be 0 or negligible. Why it is so? If this is my voltage B and this is delta B, this is E, then you can see here that this is the in phase component and this is the phase quadrature component. Okay, so this component has less effect on the magnitude of the voltage. If I know the real component of this, okay, if we know this component delta Br, this is delta Br, this is delta Bx, let's, for example, and this is delta B, then delta Br has more effect on E rather than delta Bx. Why? Because B plus delta Br is approximately equal to E. And we can say, since this angle is small, since delta is small, so we can say delta Bx will not be affecting much the magnitude. So we have ignored the delta Bx part here. Okay, we have taken only in phase component and we replace the value of Rs and Xs. Once we do this, then we can find out the value of this delta B by B. So this becomes B square, and here it is ZSC cos phi SC. Now ZC is common. Okay, so last time we proved ZSC is nothing but E square by SSC. So this is E square by SSC. And then we have a B square also because of this. So this is B square. So E square by B square phi SSC into PL plus sin phi SC into QL divided by SSC. Now again, normally during fault conditions, the reactance of the feeder is quite high as compared to the resistance. So I can say the XS is quite high than RS. And hence the angle phi SC is quite close to 90 degree. Because of that, the cos phi will be 0, this will be 0, and this will be 1. So we can say that E square by B square into sin phi SC or QL by SSC. So this becomes as a simplified expression as delta B by B equals E square by B square into QL by SSC. Also, to simplify further, we will say that E is approximately equal to B. Now here is a confusion. You may say, if the E is approximately equal to E, then why we are solving it? Okay. Well, this is one way of doing the things, that we approximate and simplify to the extent possible and see what it gives to us. So we are trying to simplify as much as possible. So looking into that aspect, we also assume that E is not very far away from B, or B is not very far away from E, and hence this equals to 1. Okay. So that actually means that this becomes 1. So delta B by B becomes E minus B by B. Delta B by B becomes E minus B by B, which is equal to QL by SSC, because this is 1. Okay, this is 1. So this becomes QL by SSC here. So it becomes 1 plus QL by SSC into B equals to E, and B equals to E by 1 plus QL by SSC. Normally QL by SSC is far less than 1, okay, less than 1. Hence we can expand by binomial expansion, and we will get as B equals to 1 minus QL by SSC, approximate relationship. Okay, you will get higher order terms, but they can be neglected. So this is close to this expression. Now this is very interesting relationship. We have some simplification, but it is very insightful result. And this will make you to understand many phenomena in the power system. Okay, you know, the Ferranti effect, the change in the voltage at the load bus, and the nature of the load. How you can interpret its meaning can be understood from this diagram. You can see here the QL, the load power, the load reactive power is varying from 0 to positive and 0 to negative. If the load reactive power is negative, this is called as a capacitive load. So this is the capacitive load and this is the inductive load. Okay. So when the load is inductive, that is QL is positive, then B will be less than E. You can see from here. If QL is positive, means basically inductive, then you see that B will be less than E. And you can see that B is reducing than E. This is the line of B. However, if QL is negative, means basically we have capacitive load. In that case, B is greater than equal to E. This is called Ferranti effect. The Ferranti effect is one which says that if the line is lightly loaded, in that case it becomes a capacitive circuit because the load is less and the ground capacitance becomes dominant, and hence the load becomes kind of a capacitance. So for that capacitive load, the receiving end voltage is more than the sending end voltage, and this phenomena is known as Ferranti effect. Alright, so remember, when we have a capacitive load, the voltage at the load bus will increase, and when we have an inductive load, the voltage will decrease. Normally we have an inductive load because we have a use of the heavy induction machines, induction motors in the industries and industrial plants. So 50 to 60% load in the power system is coming from the use of the induction motor, which is inductive in nature. So mostly we have a less voltage in the power system. Alright, so this explains the relationship of the voltage variation. So for a capacitive load, you can see the voltage at the load bus is going up. Therefore, if you want to compensate inductive load, you have to add the additional reactive power which increases the voltage. And if you want to compensate capacitive load, you have to increase the reactive power of the inductive, so that it compensates the nature of the load or compensate the reactive power of the load. Obviously, if you have more inductance on the load side, you have to put capacitance bank to control this voltage. And if you have a capacitive load, you have to put inductance to control the voltage or even power factor. We will understand this phenomenon with the help of example so that it's more clear that what is the meaning of this relationship and how we should use for analyzing the power system or distribution network. This example is example 1 of the 4th unit of the NPTEL book that I have given you, and in this we have to find out the voltage at the load bus, okay, and the voltage drop and the system voltage without any compensator first. And then we will find out that if we want to maintain the bus voltage, the load bus voltage as the source voltage, what should be the capacity of the compensator. And in third, we will find out what will be the voltage at the load bus for unity power factor compensation and what will be the rating of the compensator. Okay, so this aspect belongs to voltage regulation, this belongs to voltage regulation, and this aspect belongs to power factor compensation. Okay, we will see one by one. Okay, so let us start. What is given to us is line to line voltage. This is three-phase system. So we are given line to line voltage of 6.9 kilovolt, 50 hertz frequency, a three-phase induction motor with a real and reactive power demand of 25 megawatt and 40 megawatt. The short circuit capacity of the load buses or the system is 300 MVA with XS by R ratio or X by R ratio as 5. Then you have to compute all these parameters. So start with the A question first. Okay. Now since it is three-phase system, either we can solve on three-phase basis or we can solve on single-phase basis. I will advise you to use single-phase basis or per-phase basis. Then you have to transform the quantity on per-phase basis. For example, the line-to-line voltage need to be expressed as phase voltage. So 6.9 by root 3 becomes 3.9837 kilovolt. Remember dimension. And the short circuit capacity per phase is 300 by 3. It becomes 100 MVA. The real power becomes 25 by 3. So becomes 8.33 megawatts per phase. And the real power at the load becomes the reactive power, and the reactive power of the load becomes 40 by 3, that is 13.33 MVA per phase. What is ZS? The short circuit impedance or the feeder impedance will be ES square by SSC. It becomes 0.1587. Now we are given the value of X by R ratio as 5. This gives the phi SC, which is tan inverse 5, 78.69, and this gives RS and this gives XS. The RS is ZS into cos phi S and XS is ZS into sin phi S. So value of RS is found to be 0.03 and value of XS is 0.15. And the value of ZS is nothing but RS square plus XS square, or you can say RS plus JXS. This is the value of ZS. The first case is when we don't have any compensator. That actually means that Q gamma equals to 0. When Q gamma equals to 0, there is no compensator at the load bus. We have to solve for only voltage. So we use the first equation that we have developed, the quadratic in QL, and solve for the voltage actually. So we have to arrange. So we will use the equation that we developed, quadratic in QL in quadratic in V R square. Okay, so we express this equation in terms of the quadratic or power of B square. So it becomes B4 and this constant into B square. This constant means C equal to 0. Substitute the value of RS, XS, PL, QL, and we can solve for voltage at the load bus. Now we solve for the voltage at the load bus. We will get this equation as the quadratic in V square. And this gives the value of V square as 10.61 and 0.5866. Therefore, the value of V will be plus minus 3.25 and plus minus 0.76. Obviously, RMS value cannot be negative, so negative values are ruled out. There are only two positive values and the maximum of positive values is considered, which is near to the rated value. So 3.25 is the correct solution. Therefore, the load bus voltage will be 3.25 kilovolt per phase. And the actual voltage at the source is 3.98. So what is voltage regulation? E minus B by E. 3.98 minus 3.2 by 3.98. The voltage regulation comes out to be 18.21%, which is quite high. That means if there is 100 volts, then there will be a drop of 18.21% or 18.21 volt. The remaining voltage will be something around 82, which is quite less, and the load connected at the load bus may not operate. So with this voltage regulation, the current can be found, that is PL minus JQL by B. We know what is PL per phase and we know the voltage, so from that we can find out the current. You can see the current is 4.82 kilo amps, angle of minus 57. Please note the dimensions very carefully. Since powers are in a mega wattage or mega volt ampere reactives and voltage in kilo, so dimension of current will be in also in kilo amps. Okay, so that has to be taken care of. Then we can find out delta V, which can be simply found by multiplying ZS and IL. This gives the value of 0.765 angle of 20.69. We can also find this value from this expression that we have developed. Okay, the value will be same. And once we know delta V, then we can compute E. E is nothing but B plus delta V. And value of E must be what? 3.98, because the magnitude of voltage at the source was fixed. That is 6 kilovolt by root 3. You can see in the beginning 6.9 by root 3. So this will be same as 6.9 by root 3. Okay. So this is 6.9 by root 3. And these are shown here. This is the B. Okay. This is the current IL. And because of this current, they drop I into R, and reactive drop I into X. This gives value of E. And this is delta Bx. Okay, so delta Br plus delta Bx, J becomes delta B, and B plus delta B becomes E. In the second case, we use a compensator as a voltage regulator. So we want to maintain both the voltage, that is the load bus voltage and the source bus voltage, at the constant value 3.98, which is 6.9 by root 3 per phase voltage, for certain value of Q gamma, such that Q gamma plus QL is QS. So we use this equation quadratic in QS, substitute the value of R, X, PL, and solve for QS. When we solve for QS, we find the value of QS as minus 194 minus 2.0421. Obviously, we will choose the least value so that the rating of the compensator is the least. So for this value of QS, we can find out Q gamma. The Q gamma comes out to be QS minus QL, and QL is 13.33, so minus 2.0 minus 13 becomes minus 15.37. This is the rating of the compensator for voltage regulation, such that the load bus and the source bus are at the same voltage. And for this Q gamma, we can find out the current I, which is PL minus JQS, because the net reactive power at the load bus is QS. Substitute here minus 2.04, and this gives the source current as 2.15 angle of 18.68. You see, the IS is leading the voltage at the load bus by 18.68 degree, and delta V for this is 0.3418. We can also verify this value from the standard expression for delta V. same as this, and the value of E is 3.98, 4.91 degree. So you see the voltage is same at both the buses. Obviously it has to be same. This voltage is same as B. But B angle is 0, 3.98, angle is 0. This E is second 3.98, angle is 4.9. They have same magnitude, but there is a phase angle shift, and the shift is responsible for transferring the power from the source to the voltage. This is a diagram for this. You can see. You can also find out the I gamma. I gamma is S gamma conjugate by B, which is nothing but P gamma plus JQ gamma conjugate. Now P gamma is 0, as there is no real component, so it becomes minus JQ gamma by B. Substitute Q gamma here, minus minus become plus here. So this is the current of the compensator. This I gamma is here. So I gamma plus IL becomes IS, this IS, which is having 18 degree from the load bus voltage. Okay, and this delta is actually 4.9 degree. This is the phasor diagram for system when the compensator is used for voltage regulation. You can also find out the power factor at the load bus and at the source bus. At the source bus, the power factor will be angle between E and IS. So that power factor will be this minus this. Okay, that is 18.64 minus 4.91. So cosine of 13.77 will be 0.97. So for this situation, the power factor will be leading at the source bus. So here the power factor at the load bus will be the angle between I and B, cosine of 18. Okay, so cosine of 18 will be 0.9473. So at the load bus we will get the power factor of 0.94 lead, and at the source well we will get the power factor of 0.97. Now the third part of this problem is to find out the voltage at the load bus when you want to achieve unity power factor at the load bus. So for unity power factor of the load bus, all reactive power at the load is supplied by the compensator, so that the power factor at the load bus becomes unity. So when you substitute this, the QS equals to 0. Okay. So using this expression for QL as 0, actually this is QS, because QL becomes QS, and this becomes 0, net power of the load is 0. So only PL is there. Then you solve for this voltage, the voltage comes out to be 3.90 at the load bus. So 3.90 is not 3.98, the exact value of E, but it is close to value of E. And with this we can find out the current P minus JQ by B, which is 4.02, angle of minus 57. Delta V is I into ZS, 0.33, angle of 69.69, which can also be verified from this expression, and value of E is 3.9. Okay, you can also find out the voltage regulation for this will be slightly better than the previous case. The power factor at the load is unity because angle is 0. However, the power factor at the source bus will be the cosine angle between E and IS. So this is 4.78. Okay, so cosine of 4.78 will be 0.9966 lag, because the current is lagging the E voltage in this case. So this is known as the power factor compensator. So we have seen that compensator can function as a power factor controller or power factor control, or it can act as a voltage regulator. If it is used as a voltage regulator, you don't have a direct control of power factor, and if you use for power factor correction, it won't have a direct control over the voltage. However, it is seen that if you control the voltage, the power factor is normally improved. Similarly, if you control the power factor, voltage is improved. Okay, so these are important conclusions. However, you cannot control two parameters independently. In the next class, we will learn how to compensate three-phase unbalanced system. First, we will consider three-phase three-wire system, and we will see that an unbalanced system can be perfectly compensated with the help of purely reactive network to achieve unity power factor at the source.